Hello friends, myself Ganeshram Girnar from R.C. Patel Institute of Pharmacy, Shirpur. Today we are going to discuss on the chapter buffers. First of all, definition of buffer that we will see, then different types of buffers we will see, and after that the very important thing in this chapter, that is the mechanism of buffer action, that we are going to see. In that, first, in introductory point, that is definition of buffer, it is nothing but it is the solution which resists to change in the pH after addition of small amount of acid or base is called as buffer. So simply you can say that it is nothing but it's a solution which is used to maintain the pH of any another solution. Second definition of this chapter is buffer capacity. It is defined as the moles of strong acid or strong base required to change the pH of 1 liter buffer solution by 1 unit. Means if you can consider any buffer solution having the pH 5, so how much amount of acid is required to convert that 5 pH to the 4, or how much amount of base is required to change the pH from 5 to 6, that amount of acid or base is called as the buffer capacity. Okay, next to that is the type of buffer. There are two different types of buffer. First is the acidic buffer and second is the basic buffer. These both types we will discuss later in detail again. Just now we will see the definitions. In that, first, acidic buffer, the solution containing the mixture of weak acid and its salt, called as acidic buffer. Example for that, acetic acid, which is the weak acid, and its salt, that is sodium acetate. After combination of these both, it gives the acidic buffer, and the name of that buffer is the acetate buffer. Second is the basic buffer. Similarly, like acidic buffer, in case of basic buffer, the solution which contains the mixture of weak base and its salt, called as basic buffer. In that example, ammonium hydroxide, which is weak base, when it combines with the ammonium chloride, its salt, it gives the ammonium buffer and it is acting as a basic buffer. Next, that is properties of buffer. As the definition suggests, the pH of that solution must remain constant. So the first property, the pH of buffer solution must remain constant. There should not be any change in that pH. If you are diluting that solution, means by adding water or any another solvent, there should no change in the pH of buffer solution. It's another property. And last property of buffer solution, on addition of some acid or base, there should not any change in the pH of that buffer solution. It remains constant, so that you can say that it's a buffer solution. So these are the three different ideal properties, or you can say the characteristics of buffer solution. Next thing, that is the what is the importance of buffer solution and why we use that buffer solution in our field. Okay, so there are some points which are going to discuss. In that, first, stability of certain compound. Certain compounds are stable in specific pH. Some compounds, in this we can take the example, that is citric acid. It is used to stabilize the milk of magnesia. Means milk of magnesia requires some acidic condition to remain stable, so you can use there in case of that citric acid to stable that solution. Second, structural stability. Compounds are structurally unstable due to autooxidation at particular pH. In that, again we can consider the example, that is sulfonamide preparations are stabilized by sodium bicarbonate, sodium acetate and sodium citrate. When we are adding this solution, then and then sulfonamides can be stable, or you can say that there is no change in the structure of that sulfonamide. So to confirm or to make the structure stable, we can use the buffer solution. Next, to maintain the color of some preparations, we require the buffer solution. Here you can consider the example of limit test for iron. In that limit test for iron, the purple color is maintained in alkaline pH, and so to maintain that pH, we use the citrate buffer by adding the citric acid. Next importance, or you can say use of buffer, that is for the patient comfort. An extremely acidic or alkaline solution, it may cause irritation to the patient or any tissue damage to the patients. So you can say at optimum pH, or at particular you have to maintain the solution pH, so you use the buffer solutions. Next to that is optimum pH conditions for activity of certain medical compounds have to be maintained, just we have discussed before that. In case of analysis, buffers of known pH are required as standards in the analytical laboratories. In that example you can consider that is 1.2 pH solution requires for the dissolution study. And next to that is the for the solubility of some compounds, that is solubility of compound is controlled by providing a medium of suitable pH. In that you can consider example of different salts like iron, phosphate and borates. They are soluble in acidic medium and it can precipitate in alkaline medium. So if you want to soluble such a salts, you have to make the acidic solution, you have to maintain the acidic pH. So that pH you can maintain by using the acidic buffer solution. So just which we have discussed, that is nothing but the importance or use of the buffers in our pharma field. Now the very important thing that we have to go now discuss, that is the mechanism of buffer action. Just we have seen that is the definition of buffer, that it's a solution which does not allow to change the pH, or the solution which resists to change the pH. So what exactly the mechanism of that solution, why after addition of some acid or base there should not change in the buffer solution? So what is the exact mechanism behind that we have to see. It's very important, mechanism of buffer action. Now again we will see, just we have discussed before, there are two different types of buffer. First is the acidic buffer and second is the basic buffer. Acidic buffer is composed of any weak acid and its salts. Example you can consider, that is acetic acid, it's a weak acid, and its salt, that is the sodium acetate. After combination of these both, it gives the acidic buffer, that is the acetate buffer. Second is the basic buffer. Again it's a composition of a weak base and its salt. In that example you can consider ammonium hydroxide and ammonium chloride. Now we will see one by one, that is first the mechanism of acidic buffer and second is the basic buffer. In that first mechanism of acidic buffer system, just we have taken example, that is acidic buffer contains acetic acid CH3COOH and its salt, that is sodium acetate, that is CH3COONA. After combination of these both you get a acidic buffer. So what happens after dissociation of acetic acid? It gives the salt, it gives the ion, that is acetate ion and H plus ion. And after dissociation of sodium acetate, again it gives the acetate ion as well as the sodium ion. As we all know, acetic acid is a weak acid, so it does not dissociate totally. Some part of acetic acid remains unionized and some part converts into the acetate ion as well as H plus ion. But in case of sodium acetate, it totally dissociated, it totally converts into the acetate ion as well as sodium ion. Now the solution contains mostly acetate ion as well as the acetic acid. Now exact mechanism is there. In acidic buffer solution, if you are going to add hydrochloric acid, means acid, so from that H plus ion from the hydrochloric acid combines with the acetate ion which are present in the solution of the acetate buffer. So H plus ion reacts with the acetate ion and it forms the acetic acid. So because of formation of acetic acid, as it is weak acid, so there is a no change in the pH. So after addition of acid, there is a no change in the pH of the solution. Similarly, in the acidic buffer solution, if we add small amount of base, so you can consider the example, that is sodium hydroxide. In that hydroxide ion, that is OH minus ion, combines with the acetic acid. As I told you earlier, in the acidic buffer system there are two main components are there. First is the acetic acid and second is the acetate ion. So now when you are adding the sodium hydroxide, that time that OH minus from sodium hydroxide reacts with the acetic acid and it forms again acetate ion as well as the water. As we all know, water is neutral in nature, so again there is no change in pH, as well as acetate ion also does not cause any change in the pH of any solution. So by that mechanism we can consider, if we are adding acid, so that H plus ion from that acid reacts with the acetate ion and it forms the acetic acid, which is a weak acid, so there is no change in the pH. If you are adding any base, so OH minus from that base reacts with the acetic acid, it forms neutral product, that is water and acetate ion, so there is no change in the pH of the solution. Similarly, same condition happens in case of the basic buffer. If you consider example of basic buffer, it is nothing but ammonium hydroxide as well as ammonium chloride. So ammonium hydroxide is a weak base, so there is no total dissociation of ammonium hydroxide. It gives some part ionized, that is NH4 plus and OH minus, and remaining part of ammonium hydroxide remains unionized, that is NH4OH. Ammonium chloride get totally dissolved. So in this basic buffer, if you add some again acid, that is hydrochloric acid, so H plus from that hydrochloric acid reacts with the ammonium hydroxide, it forms NH4 ion, that is ammonium ion, as well as water. Again, as water is neutral in nature, there is no change in the pH of the solution. And secondly, in case of same, that is in basic buffer, if you are adding any basic compound, so in case of basic buffer solution, if small amount of base, that is sodium hydroxide, is added, so hydroxide ion from that base, that is OH minus ion from that base reacts with the ammonium ion, that is NH4 ion, and again it forms the ammonium hydroxide, which is the weak base. So again there is no change in the pH of the solution. So both mechanisms are same, that is if you are adding H plus ion or if you are adding OH minus ion, it forms either water, that is neutral solution, or it forms any weak acid or base, and so that there is no change in the pH of that solution after addition of some amount of acid as well as base. So this is the mechanism of acidic buffer as well as the basic buffer. And the pH of buffer solution can be calculated by one equation, that is known as Henderson-Hasselbalch equation, and that equation is the pH is equals to pK plus log of concentration of salt divided by concentration of base. pK is nothing but the dissociation constant. Next to that, two types of buffer, just we have C, acidic as well as basic, but there are two different types, that is physiological buffer and standard buffer. Physiological buffers, that is nothing but which are present in our body, and because of that our body pH or our blood pH remains constant, that is 7.3 to 7.4. And now we are focusing, that is the standard buffer solution. These are the buffer solution which varies pH from 1.2 to 10 pH, and these preparations are used for the different studies to maintain the pH for different studies. And the different standard buffer solution you can see, that is the hydrochloric acid buffer, which have the pH 1.2 to 2.2. Second, that is the acid phthalate buffer having the range 2.2 to 4. Neutralized phthalate buffer having the pH range 4.2 to 5.8. Phosphate buffer, that is 5.8 to 8. And last one, that is the alkaline borate buffer having the pH range 8 to 10. Method of preparation is also given, that is not that much of important, but you can take a look for that method of preparation. In this total chapter, the very important thing, that is only the mechanism of buffer action that we have focused mainly. Remaining part you can understand very well. Okay, so this is all about the different types of buffer. First is the definition, then different types of buffer, importance of buffer, as well as the mechanism of buffer, and different standard buffer solution that are known as the official buffer solution. This is all about the buffers. Thank you very much for listening. Thank you very much.